Let's look at OpenStax University Physics Volume 2, Chapter 13, Problem 30. A long solenoid with n is 10 turns per centimeter has a cross-sectional area of 5 square centimeters and carries a current of 0.25 amps. A coil with 5 turns encircles the solenoid. When the current through the solenoid is turned off, it decreases to 0 in 0.05 seconds. What is the average EMF induced in the coil? So let's write down our knowns and unknowns. We know that n is 10 turns per centimeter for the solenoid, and we have to convert that into turns per meter. We know that the area of the solenoid is 5 square centimeters, which we'll have to convert it to square meters. It carries a current I of 0.25 amps. A coil with n equals 5 turns, so this is n coil, is wrapped right around the solenoid. And then we're turning the current off. So in delta t equals 0.05 seconds, the final current is going to be 0. So I'm going to call the other one I initial. And we're looking for the EMF induced in the coil as the current is going to 0 in the solenoid. So let's draw the diagram. We have a solenoid that looks somewhat like this, and around the solenoid there is a coil of 5 turns that's wrapped right around it. It's hard to see what's going on here, so I'm going to draw a cross section through this and have the solenoid look like that. So I have current coming out on the top, let's say, and in on the bottom through all these coils. And then the coil is going to be wrapped right around the solenoid. So we're looking for an EMF, which means that the EMF in the coil is negative N coil delta phi b delta t. So we have to use Faraday's law. So that is negative N coil delta phi b. So the magnetic flux is BA cosine theta divided by delta t. And then we have to stop and evaluate these things. Is the magnetic field changing? Well, not directly, but magnetic field has a current component in it. So the current is changing, which means that the magnetic field will be changing. Is the area changing? No, the area isn't changing. It's the area of the coil, and it has this value that's given over here. Is the angle changing? So the angle would be the angle between the magnetic field and the area, and that is not changing. Both of them are staying in the same direction. The magnetic field through the solenoid will either be to the right or to the left. The area vector for the coil is going to be either to the right or to the left. We don't know exactly what the direction of the current is, and it doesn't matter for this problem. We're just looking for an average induced EMF. So that means that we're dealing with cosine 0 here, which is 1. So since the area is not changing, I'm going to take it outside of the delta symbol, and then I have negative N coil times the area delta B delta T. Now, the magnetic field is a magnetic field that goes through the coil, but it is caused by the solenoid. So the solenoid is the thing that has current going through it, so it's the magnetic field of the solenoid that we're dealing with. So then this becomes negative N coil times the area of coil and solenoid, and then we have delta mu naught N solenoid I divided by delta T. We know that mu naught and N don't change, so we'll take these out of the delta symbol, and then we'll have negative N coil A mu naught lowercase n delta I delta T. So that is negative N coil area mu naught N. Delta means final minus initial. So I have I final minus I initial divided by delta T. So now I have all of these quantities in my knowns. I can plug them in. So it's negative 5 turns in the coil. The area is 5 times 10 to the negative 4th square meters. Mu naught is 4 pi times 10 to the negative 7 Tesla meters per amps. Lowercase n is 1000 turns per meter. I final is 0, I initial is 0.25 amps divided by delta T, which is 0.05, and we get 1.6 times 10 to the negative 5th volts for the induced EMF in the coil.